Chapter 14, Kinetics, Exercise 14.39. This graph shows a plot of the rate of a reaction versus the concentration of the reactant A for this reaction from A to products. The reaction rate is proportional to the concentration. So we can write out this. A is proportional to the concentration, therefore A is a constant times the concentration of A. And this is a first order chemical reaction. First order. Because R is proportional to A to the power of 1. Choose a rough sketch of A versus time. So first, A is the reactant. Therefore, the concentration of A decreases with time. The first graph, this graph is wrong. The second graph, the concentration of A decreases with time in this plot. However, it's still incorrect because when we have first order chemical reaction, the concentration of A decays exponentially. Let me give you the equation. The concentration of A at time t is equal to the concentration of A at time 0 multiplied by e to the power of negative kt, where k is the reaction rate constant and t is the amount of time. Apparently, this is not a linear equation of time. Now let's look at this plot. It's reasonable. It decays in a curvy fashion, but so is the last one. This one might also show the exponential decay or exponential decrease of A. So which one is correct? It's hard to tell, but based on this equation, we can determine the half-life of A. That is when this A reaches 1/2 of the initial concentration. So when this A reaches 1/2 of the concentration, we can determine the value of T. We cancel this A naught and A naught, and we have this equation. Now we take the logarithm of both sides, and we get this is equal to negative kt. The natural logarithm of 1/2 is negative ln2. Alright, so we'll deal with this equation. The negative sign and negative sign cancel. So T should be ln2 over K. This is how we find the half-life of the concentration of A. Now, what is K? K can be determined from this graph. But how? Well, we know that the reaction rate is K times A, right? So K is R over A. So we have this equation. K is R over A. Now, how do we use this graph to compute R over A? Well, over here we have a line, but you can use any data point on this line. I'm going to use this data point right at the end. R is 0.012 and A is 0.6. Do the division, we get 0.02. So K is 0.02. The unit is second to the power of -1. Now we just need to plug in this value here to find the half-life. This is going to be the half-life. Alright, and 1 over second to the power of -1 is just second. So again, this is the half-life, and this is in the unit of second. The value is 35 seconds. So the half-life of A is 35 seconds. Let's take a look. We have this graph, we have this graph. In this graph, the half-life is roughly here, more than 100 seconds, all right? Because the initial concentration is 0.6. And at the half-life, the concentration is 1/2 of 0.6, 0.3, and this is roughly 0.3. But this is more than 100 seconds. We got 35 seconds. So it's got to be this option. 0.3 less than 100 seconds. Although even this graph is not very accurate. So supposedly at 35 seconds, the concentration, so it's around here, the concentration should drop to 1/2. So it should be like this. That would be more accurate. But anyway, this data plot looks better than this one because this one indicates the half-life is more than 100 seconds. In this one, the half-life is less than 100 seconds. Part C. Identify the rate law. It's a first-order reaction, so the rate is K times a to the power of 1. Part D, estimate the value of K. I think we did that because for the first order reaction, we have R is equal to Ka. And the value of K is R divided by, so K is R divided by the concentration of A, and we had this graph. When A is 0.6, R is 0.012. So 0.012 as the value of R, 0.6 as the value of A, and when you do this, you get 0.02. The unit is going to be molar per second divided by molar. So over here, the answer should be 0.02 per second.